In this work, we address the problem of enabling accurate and robust lidar odometry for autonomous robotic platforms involved in exploration of extreme environments, such as those found in mining, search and rescue, and planetary exploration missions. In these scenarios, such as what you see here, onboard sensing faces severe perceptual degradation from conditions such as obscurance, self-similar areas, jerky sensor motion when moving over rough terrain, and even loss of individual sensor modalities. This makes robust multi-sensor fusion a vital step towards achieving accurate operation in these perceptually degraded settings. While there have been many multi-sensor algorithms proposed that can achieve great accuracy, what we focus on here is the performance and the robustness under perceptual degradation. To address these challenges, we present LOCUS, Lidar Odometry for Consistent Operations in Uncertain Settings. This is a multi-sensor, Lidar-Centric solution to real-time SLAM. We will show here how it can achieve top-class localization accuracy in perceptually degraded settings and is robust to sensor failures. LOCUS has been deployed on heterogeneous robotic systems in the DARPA Subterranean Challenge, where it was able to be part of Team CoStar's solution that won the urban circuit. The proposed system can take a generic number of LiDARs and puts these through motion distortion correction steps. These are then fed into a point cloud merger to have one point cloud, which is then filtered to remove outliers and reduce the size of the LiDAR to manage computational load. This then goes into our scan matching unit to do the LiDAR alignment. However, one of the key components of this is our injection of external sensor modalities, such as visual odometry, wheel odometry, kinetic odometry, and IMU. These go through our sensor integration module that produces a robust seed to our ICP method of scan alignment. This sensor integration module is also health aware. It looks at the different input sources, their covariance, the rate of input, and custom health metrics depending on the algorithm. With these, it puts out the most robust seed it can get to the scan matching algorithm. It does this with a priority queue, where we first consider the highest accuracy source, such as wheel inertial odometry. If that's not healthy, then it will consider the next highest priority source, for instance IMU. And if that's not healthy, it will revert back to just an identity guess. The robust seed seeds the scan-to-scan matching for sequential LiDAR scans, which then seeds a scan-to-submap matching, the output being the odometry and the updated map. We evaluate LOCUS against the state-of-the-art in open-source algorithms. This is listed here. These algorithms cover a range of different approaches to multi-sensor LiDAR-centric SLAM, including different methods of integrating additional measurements, being tight integration of IMU, loose integration of odometry, different ways of doing alignment, such as with GICP, with optimization approaches, and different features that are being matched. We evaluate these on a dataset from a ClearPath Husky using 2 LiDARs and an IMU, as well as wheel odometry. There are datasets 2 in an urban environment in the SATSOP's power plant, and 1 in a mine in the Brewston Safety Research Mine. These are from the DARPA Challenge. These contain some perceptual degraded conditions such as self-similar environments, obscurance, and very rough terrain that leads to jerky sensor motion, especially with this skid-steer wheeled robot. First, we look at an accuracy evaluation, starting in the alpha course of the urban environment. Here, each of the algorithms are performing well. On the bottom right, you see the view looking forward from the camera of the robot. Cartographer starts to drift slightly. But overall, most algorithms are performing well. LOCUS has the best map error at 0.29 meters and the best odometry error at 0.62 meters. Next, we look at the beta course. This is in the urban environment as well. And we introduce LAO mapping in this comparison, which you see in the middle, on the top. LAO mapping, while performing accurately, has a large delay with large computation times, so it's not able to operate in real time. However, all algorithms perform quite well on this dataset. LOCUS still has the best map error at 0.69 meters and the best odometry error at 0.88 meters. Finally, we look at the safety research course. This is in a mine. This is a larger scale than the other tests, and we use LAO-SAM here, which you see in the bottom in the middle. All algorithms perform well at the start. However, the robot returns to some self-similar areas and goes back and forth in that area, with some large rotations as well. This causes issues for ALOM and cartographer. As the robots continue to the furthest extent of exploration, BLAM in the top right has some issues with the rotational error. However, LOCUS and LAO-SAM still perform well and are very consistent. In this course, LAO-SAM is the best performing, but with equivalent performance from LOCUS. The map error for LAO-SAM is 0.52 meters, whereas for LOCUS it's 0.63. And the odometry error for LAO-SAM is 1.26 meters compared to LOCUS at 1.67 meters. In this graph, we summarize the overall odometry accuracy for the different methods in the different datasets. And what this shows is that LOCUS has top-class performance in localization accuracy for each of these challenging environments. Next, we look at the robustness evaluation, where we simulate drops in different sensor modalities. First, we look at a drop in wheel inertial odometry, which affects LOCUS and cartographer. LOCUS will simply step down to using only IMU as an initial guess and continue unharmed. Cartographer has a synced callback though, and hence stops operating entirely when one of the inputs to that synced callback is no longer coming through. Next, we look at the drop of both wheel inertial odometry and IMU. Here, we look at LOO mapping, a tightly integrated method. And this result is the same, where LOCUS can gracefully come back to a purely Lidar odometry, whereas LAO mapping has a synced callback and stops operating entirely. Finally, we look at the drop of the most fundamental sensor source, the Lidar. We simulate a 10-second drop in the Lidar and see how that impacts the algorithm performance. What we see is that LOCUS is able to accumulate wheel inertial odometry over that period, and so when the Lidar returns, it is near to its correct position, and so the point cloud alignment from there forward is accurate. Other algorithms are not able to do that. They either rely on IMU integration or no information. So when the Lidar returns, there is a large error in that resulting point cloud alignment. Next, we look at the efficiency analysis. And here we see that LOCUS is able to perform at real time below 0.1 seconds per LiDAR scan with our 10 Hz LiDAR scans throughout the different operations of these environments. Thank you, and we would like to refer you to our paper for more details. Thank you for watching the video.